All right, guys, for this playlist, I'm just going through pre-solved problems for the sake of time. I know you guys have a lot to review for the final, so hopefully this gives you a chance to see more problem examples. So this first one that we're starting with, the essential point of this problem is to figure out the B field due to a current moving through a wire. There are two different ways to solve this problem. We can either do A by finding the vector magnetic potential A, and then B by applying the Biot-Savart law. So we're going to look at it both ways, just kind of from a high level here. So this is going to be really important because we're going to recycle the solution to this equation in a lot of different problems in chapter 5. You'll have a lot of different problems where you have wires in different configurations, and you can use this base equation for B field due to a wire and manipulate it for different problems. So this problem is very key for a lot of things in chapter 5, okay? So just knowing the general solution for this problem is key for a lot of things in chapter 5. Okay, so first, part A, finding the vector magnetic potential, and then using that to find the B field. Okay, so vector magnetic potential, we have a general equation here. This is just some derivation kind of stuff. You can look at the chapter itself. But basically, the important pieces that we need to find A is we need to find our DL element and then our R element. So DL is going to be along the current direction, okay? And in this case, when we're looking at our current, we're changing in the Z direction, right? So we're moving this way. So we have change in Z, dZ, and it's in the Z hat direction, the positive Z hat, because we model the current direction as going up. Okay, so in this case, dZ in the Z hat direction. So change in Z towards the positive Z. Okay, now we need to find our R value here. So for our R value, in this case, for this particular problem, we are looking at this right here. So the problem is asking us to find a B field at a certain distance R away from a wire. So we're just a certain distance away, right? And so we are basically just Pythagorean theorem here, where we have this Z prime and then this R, this little r, the distance away, and we're finding the vector from the charged element to our point. So we need to model it with this little differential Z here, okay? So Z prime squared plus R squared. So we're just going to plug that into our denominator. And then we need our bounds for dz here, okay? So for this wire, for the bounds for our z, we're going from negative L down here to positive L, okay? And this L can be any length. When we solve for this problem, we're essentially going to end up with an equation that's going to let us plug in different small r values and different large L values to solve for B field due to a wire of different lengths, and then to find a B field at different distances from that wire, okay? So plugging in everything that we have and our bounds here, we're just basically integrating. So the integral of this guy is going to turn into this here. So we're plugging in negative L and L, and we're going to end up with Z prime plus the square root of Z squared plus R squared, just for integral, and then from negative L to L. And then we plug in our answer here, and we end up with our A, okay? So I'm skipping a lot of the basic math here, so please go through this problem and try it yourself. I know you guys did this for the homework, so I won't hit it too hard here. Okay, so after you find this A, you're finding your del operator cross A to find your B fields. Okay, so this is super similar to divergence in Stokes, specifically to Stokes. In this case, we have an A in the Z hat direction, okay? So, and we're dealing with a cylindrical coordinate system. So we're going to take the cylindrical del operator cross A, look at this piece, and then just plug in the pieces that we have, okay? So very similar to Stokes, basically canceling out everything that we don't have. We're plugging in the pieces that we do have. We notice this term goes to 0, okay? And then we are, because we don't have anything in terms of, yeah, when we solved for this guy, right? Yeah, we don't have anything in terms of z, we just have an r component, so that's why we have this one. Okay, so then we take our partial derivative here, and after we do so, our final solution is just this for our b. So we're basically just recycling this for different problems. So the important takeaway for this is that we have two conditions where we're using this equation. The first condition here, we can use all the time. The second one, we have when the R is significantly less than L. So when we're modeling L as some kind of an infinite wire, where it's just very, very long, okay? And in this case, we can drop out these two terms, not necessarily infinite, but like semi-infinite. So just like a wire that's going on for a long time. And we can model the B field as approximately this. So we'll see a couple of different examples for this type of approach in the later problems.